What's up, everybody? Today I decided to kind of start in on the cell respiration presentation. Um, Normally I'd be doing this with you in class, but with coming back from a break, I was like, I could try calling a Zoom all of a sudden. Just didn't seem like the right thing, but I still wanted to make some progress here. Tomorrow in Zoom, we'll be going through questions from the sheet that I gave you right before break, as well as continuing on in the presentation if we have time for that. But I didn't want to waste any more time. So here's the video. I'm just going to get rolling. You'll be able to ask questions about things from this video because, again, it's based on the presentation. Shouldn't be too bad. So let's see what we've got here. Chemoheterotrophic energy processing. Ooh, fancy words. Chemo is telling us chemicals. Heterotroph, we've heard that before. Those are going to be our consumers, things that need to take in other organisms or things to get their energy. So chemoheterotrophic nutrition is the idea that you're going to get your food from another source, heterotrophic. It's going to be in the form of chemical bonds. So the bonds of your food or whatever materials are being used. And that's how you're actually going to be processing the energy for your system. We'll then incorporate that into ATP. And this is the process of how the energy goes from your food source into ATP form that your body can then use to couple all of its reactions together. So let's take a look at what we've got here. How do living systems process energy? Well, quick recap on energy in general. Food gives us our energy. We break energy out of the bonds of other molecules and then couple those into our ATP, which our body then couples into other reactions. So very heavy on our thermodynamics there with energy being transferred, not created or destroyed. There's a reciprocal relationship between chemoheterotrophic nutrition and photoautotrophic nutrition, or between cell respiration and photosynthesis. And that is that the inputs of one are the outputs of the other. If we look at our little diagram here, we can see that with water and carbon dioxide going into our plants, they're then going to break those apart. And with the addition of energy from light, rearrange those molecules to make glucose and oxygen. Now look at this for a second. CO2 and H2O is turning into C6H12O6. Okay, well, I'm going to need 6 carbons. Cool. I will get those carbons from my carbon dioxide and use that for those. Okay, what about my oxygen? Oh, well, oxygens I'll be taking from and adding in there as well. Oh, but I need my hydrogens to be able to make glucose, and I'm going to need twice as many as my oxygens or carbon. Cool. It's right here, and we'll use that right there. Yeah, but you said it's going to make organic molecules. I should use a different color here. You said it's going to be making organic molecules and oxygen. Yeah, well, here's my glucose right there. And the only thing left that I didn't use is that oxygen right there that will end up getting used as a waste product. That's the oxygen being produced. Oh, okay, cool. So I get what photosynthesis is doing. Right, but then your glucose and your oxygen will be used in cell respiration. The glucose will be the source of your food, or I should say the source of your energy as food. We'll be breaking the bonds of that glucose apart. We'll be using the oxygen to gain access to the mitochondria and snap up all those bonds in our glucose and utilize them to generate our ATP. And surprise, cell respiration happens to produce carbon dioxide and water. So this is a process that feeds itself. Photosynthesis makes the stuff that feeds cell respiration, that feeds photosynthesis, that feeds cell respiration over and over and over again in a repeat circle. So you'll often hear people talk about the relationship between photosynthesis and cell respiration, and it really is just this simple idea that the things that get made in one happen to be the reactants necessary for the next process that happens to make the reactants necessary for the next process. Good times, guys. So if we look at our, wow, these subscripts are, anyways, you can see what we've got here. We can make this very clear and easy. The things that go into cell respiration were the things that were made in photosynthesis. And the things that were made in cell respiration are the things that go into photosynthesis. So like we just illustrated above, these reactions literally rely on each other. They're based off of the, well, maybe not based. They're relying on the other one happening to be able to get its own reactants again. So these processes need each other. They're both necessary to keep that flow going. If one of these reactions were to stop completely, everything would end up dying. So if photosynthesis completely stopped, if we killed all of the plants and we did not have a way to do artificial photosynthesis, everything on Earth would die. Now we could die, every single animal on Earth could die, and your first thought might be, yeah, but where are they going to get the carbon dioxide that they need? Well, it turns out that plants also do cell respiration. Plants also have mitochondria because after they make the food in photosynthesis, they then have to break it down and utilize it to be able to turn it into ATP for their own system's use. So plants are doing both of these processes. Plants, there could be a plant planet that has nothing living on it other than plants, and it would survive completely fine. But it would be completely impossible to have an animal planet. Yeah, sorry to the cable channel, Animal Planet. Impossible to have a planet of all these animals that would be able to survive without that input of energy. And since animals can't harness that solar energy, that whole situation would be a no-go. Let's see. Metabolic reactions are tightly controlled and multi-step metabolic pathways. This is very important. You have a ton of energy. You're made up of a bunch of molecules. So they're all put together with bonds, which means technically there's a ridiculous amount of chemical energy in you. We have stored fat, you know, like fat, like this stuff. Fat, stored energy. Well, you might go to the gym and try to work out to lose weight. Oh, I need to burn this fat. Yeah, you can do work and get rid of that by utilizing that energy. But notice that the way to get rid of it is utilizing that energy. You doing enough work to actually get your body to properly break the bonds under a controlled reaction and provide that energy to your cells. What we don't see is, oh, well, let's just get all of the bonds in all of these fat molecules to just break all at once. If you did that, there would be a mushroom cloud over the gym. You release too much of that energy at any given time, and releasing energy is releasing energy. It doesn't matter if it's an explosion or breaking all of the bonds in your fat molecules. It's a ridiculous amount of energy that would be released, and believe me, things would happen. So the key with metabolism and our cellular reactions is we need to organize this in a certain way so that as these bonds are broken, we can efficiently couple the energy from those food bonds into the bonds of our ATP. So what you're seeing here in this picture is a little bit of a, I guess there's a little foreshadowing here. We can see the electron transport chain and a bunch of ATP getting made. We can see that we start by breaking apart water. Up here at the top, we have our hydrogens and our oxygens. And at the end, it gets returned to being H2O again. That's part of why we say cell respiration produces water, because technically we started with the components of water and end up reassembling it into a water, because that's a type of waste product that's easy to get rid of and non-harmful. So if that's what your body can do with the things that are left over, sweet, that's actually kind of beneficial to us. So the reason that we say, we have a little bit of a video here. The reason we say that these reactions need to be tightly controlled is because if they are not, things like this may happen. Oh no. Oh, I'm sorry, guys. The video's not showing because I'm on my laptop, but this will play in the presentation. You can go check it out later. Foreshadowing. Ooh, what's going to happen? I see a guy with a little excavator and some peeps and a fume hood. He's wearing goggles. Yeah, you guys will see. But the point of this video is they're using a strong acid to break the bonds in the sugar that's making up these peeps. And in doing so, when all of those bonds break at once, you will see what happens. Yeah. Redox reactions. Oxidation reduction. Whether you understood this in other things in the past, like in chem, I don't know. But in biology, we're not going to get too crazy with it. Here's the idea. This picture right here kind of sums up what we're referring to when we say oxidation reduction reaction or redox. Something is going to become quote unquote oxidized and something is going to become reduced. It works like this. Something's going to be receiving an electron and something is going to be giving the electron. If you are the thing that gives the electron away, you become oxidized. Your charge becomes more positive. That negative electron you had has been removed from you, and therefore your overall charge has been changed. You're no longer as negative as you used to be. We took a negative electron away, so your charge becomes slightly positive. For our chlorine here, we can see that as that electron is absorbed or taken, the thing that gains the electron becomes more negative. That's because we gave you something, that electron, that represents a negative charge. So as you accept the negative thing, you also accept its negativity. And we say that you are reduced because if you become more negative, your number or charge would go down. And therefore the term reduced is what we're looking for here. We mostly are, that's pretty much the only reason we're going to be using it in biology. We're not going to be like calculating things based off of it. But the main idea that we're looking for is with oxidation reduction, the thing that is being reduced is the one that accepts the electron, and the thing that is being oxidized is the thing that gives the electron. All right, we lost our feed there for a moment. But the big thing you're seeing here is that electrons are being transferred. Our oxygen, in this case, is being reduced as it's accepting. Here's the reason that we're talking about oxidation reduction. Electron shuttles. We have certain molecules that get used in photosynthesis and cell respiration, and their whole job is to move a charged electron from one place to another. Think of it like if you had a cooler, like something you put cold stuff in or hot stuff in. I'm sure you may realize this, but coolers keep things hot as well. For example, I've had it before, like family holiday kind of stuff, and somebody was like, you make the baked potatoes. And it's like, okay. So I make a bunch of baked potatoes in my oven, they're in foil and stuff, and I throw those into a cooler, which is actually going to maintain the high temperature in there and keep these potatoes hot on the entire trip over to grandma's house. And then by the time we got there, they were still actually pretty hot. They threw them in the oven for like 5 minutes, which really probably didn't do anything. And they were like, oh, they're done. Yeah, sweet. But it ended up holding that energy on those potatoes. The energy was maintained, all that thermal energy in those potatoes, because the container that it was put in helped hold it there. These molecules, and If we zoom in here, oh, maybe I can't do that. There we go. These molecules that we're talking about are going to be this guy, our good buddy, NADH. And in photosynthesis, we'll see another one, NADPH. There's also another one, FADH2. We'll be talking about these guys as our electron shuttles, and their main job is going to be take an electron that was charged up with energy and deliver it to a different part of this reaction. All of these reactions, photosynthesis and cell respiration, are multi-stepped reactions. So the key to this is going to be pick up that energy, that energized electron, bring it to the place where we want to use this energy, like we're charging it up in one place, but then coupling it into a reaction that's in a different place. So I need something that's going to carry this charged electron from one part of the reaction to the next step of the reaction. And that's what these electron shuttles are going to be for. So you'll hear us talking about this, but that's the main idea behind what these things are. It'll make a little bit more sense once we are looking at it in process, I guess. So electron shuttles, compounds that store electrons from our food. Again, that's because that's where we're getting the energy from. They exist in oxidized and reduced forms. So in other words, having the charged electron or being empty and not having the charged electron. Being empty or not having the electron would be oxidized. Having the charged electron, because we're adding that negative thing to you, is what we would call the reduced form. In cells, electrons come with protons, and we'll actually be separating these. That's how we will be oxidizing and reducing things. Transfer electrons and protons to other areas of the cell to continue metabolism. That is that main point we were making again. It's going to be carrying them from one part of the reaction to another. We got our two main forms here. We have NAD plus and NADH as our two forms here, and FAD and FADH2 as our forms at the bottom here. The one that we're going to see the most often is going to be NADH. Here's why NADH and NAD plus kind of work out. NAD plus. Well, actually, let's figure this out first. A hydrogen. If you were to look at a hydrogen on the periodic table, you would see that its atomic mass is about 1, and it has 1 proton. Okay, so 1 proton. Well, that proton has a positive charge. Well, that means that it's also going to have 1 electron that has a negative charge. If I were to separate that 1 proton from the 1 electron, in essence, I've kind of wrecked my hydrogen. It's weird to think about, but hydrogen is literally a proton and electron hanging out. That's the whole hydrogen. So what we're going to be doing here is dividing the proton away from the electron. So when I look at this form, NAD plus, what I actually have is NAD, and that plus is actually representing the proton that I have. Where's my text? Proton. That's what that plus sign is representing. Now, if I were to take a charged electron charged electron charged up from the energy of food bond molecules, and I add an electron to that proton that is hanging off of the NAD, it turns into this situation right here. If I have a proton and I give it an electron, that proton and electron together equal hydrogen. And that is why that is now represented with an H. So we're saying the low energy, uncharged form, the empty energy shuttle, is going to be called NAD+. That's going to be NAD and just a proton. When I provide it with the charged up electron that I want it to move, that electron plus that proton go together to be represented as a hydrogen. Because again, like we showed up at the top, hydrogen is pretty much just a proton and electron. So if you see NADH, you should automatically know, the electron has been added. I know the electron has been added because this says hydrogen now. That means that there's a proton and an electron. That's the charged version. And if you were to see NAD plus, you should know, that's the discharged version. I know there's not energy in this because it only has the proton. It didn't get the charged electron yet. Oh, how do you know that it only has the proton? Because it's represented by that plus right there. Well, how do you know it doesn't have the electron? Because if it also had the electron, one proton and one electron equals hydrogen. So if it had the electron, it would be listed as a hydrogen like it is on the right side over here. So NADH, charged up version, has the electron. NAD plus, empty version, low energy, has not received the electron yet. And pretty much what these guys are going to do is pick up a charged electron from the beginning stages where we're breaking your foods apart and carry it to a later part in cell respiration where we actually utilize that energy to charge a bunch of ATP. That's about as far as I'm going to be able to make it with you guys today. I'll be posting this video up. Actually, I think I might try to load it into Edpuzzle. We'll see. Either way, this is going to get put up for you guys today. You guys just be checking out some stuff that has to do with the presentation. And that's about it. So hopefully things are good. Hopefully your Thanksgiving was good. And I'll catch you guys next time. Bye.